Hello students, welcome to the course Verilog HDL. So far in behavioral modeling, we have understood what is meant by initial and always structured procedures and also blocking and non-blocking procedural assignments. Okay. So in this video, we'll understand the timing controls exercised in behavioral modeling. Okay. Various behavioral timing control constructs are available in Verilog. So in Verilog, if there are no timing control statements, the simulation time does not advance. Okay. And the timing controls provide a way to specify the simulation time at which procedural statements will execute. As you have seen in gate level modeling and data flow modeling, so how we are assigning delay to the statement the same way in behavioral modeling. So this is the part we'll explain you about delay specification to a statement. Okay. So there are three methods of timing control are there. So we are going in detail with this. So first type is called as delay based timing control. Second one, event based timing control. And third one, level sensitive timing control. Okay. So again in this, there are many subclasses are there. In delay based, we have regular timing control, intra-assignment control, zero delay control and all. Similarly in event based also, we have different subtypes, and finally we have level sensitive timing control. So this is the topic our interest today. So we are going to exercise each one of these with an examples. Okay. So first one we'll consider the delay based timing control. Okay. Delay based timing control in an expression specifies the time duration between when the statement is encountered and when it is executed. Okay, almost similar to data flow modeling what you have seen. So delays are specified by the symbol hash. So this was there same in there also. So this is the symbol. Syntax for the delay based timing control statement is shown below. Okay, so this is a lengthy expression. Okay, so what is trying to understand here is the delay value can be specified by using unsigned number. Just a number you can write after a hash, or you can give a parameter identifier. Some parameter you have defined, and that parameter you can write it as an after hash. Then specification, parameter identifier, minimum, typical, max expression. Okay, so all these different variants also you can use. Okay, so to understand this, we will see the examples. Okay, so then it will be better understood to you. Okay. So delay based timing control can be specified by a number. Okay, that's what I shown you there. Number, an identifier, or a minimum, typical, max expression. Okay, anything it can be. That there are three types of delay control for procedural assignments. Okay, so they are the subtypes as I mentioned. In delay based timing control, we have regular delay control, intra-assignment delay control, and zero delay control. Okay, so we'll understand this one by one, and that completes the discussion on delay based timing control. First one, regular delay control. Regular delay control is used when a non-zero delay is specified to the left of a procedural assignment. Previous video we have seen what is procedural assignment, blocking and non-blocking assignments. Okay, so it is a statement, right? For that, if there is a non-zero delay is to be specified, okay, so then regular delay will be used, and usage of regular delay control is shown in example below. So these are not just complete example. Next video, next slide also it is continued. So initially, okay, not complete program also I am not showing. Okay, module declaration of ports, that part I am not showing. Only the parameter declaration and then the initial always blocks. That is related to behavioral modeling only, explaining in example. Okay, in real time examples we will consider completely. Okay. So parameter latency. So parameter is a data type, right? Global constant. It is defining a variable latency which is equal to 20. Okay. Similarly, parameter delta, okay, equal to 2. And along with that, there are some variables also declared x, y, z, p, q. Okay. So now this we will use it in programming. So we'll write an initial block. So initial. So note down this. Okay, whatever I'm saying, try to note down. Pause the video and note down. Okay, simply just listen. Okay. So first statement you have x equal to 0. That means there is no delay here because hash symbol is not there, right? So next statement you came with hash 10, which is nothing but a delay. Okay, so y equal to 1, so delay control with a number. So we are going to show you how different ways we can specify the delay here. Okay, so number is specified here. Okay, 10. So this delay execution of y equal to 1 by 10 units. Okay, delay of 10 units it will take. See here, this is the another one, identifier. Delay control with identifier also we can use. This latency is defined earlier as a parameter which is equal to 20, right? So that we are using here, that is also allowed in Verilog. So z equal to 0 will be executed with a delay of latency number. Okay, latency how it is declared, 20 units. That's why it will take a delay of 20 units. Similarly, you can use an expression also. Okay, so latency plus delta. So here delta and latency will act as the operands and plus will act as the operator. So this combination is called as an expression, and hash symbol for p equal to 1 to execute. So this is used, okay, just to show you various way how we can specify delay control. So this is called as delay control with expression. Okay, so it is 20 and this is 222 delay units to show that it is written like this. Okay, then y x equal to x plus 1. See here, after hash y is written, that means delay control with again identifier here. Okay, so where is the value here? Y equal to 1, it is there here, right? So now y is having the value 1, which is equal to hash 1. Instead of that, you can write hash y also, that is allowed. Okay, so the different way of exercising delay, okay, we are discussing. So then minimum typical max expression also we can write like this. Okay, q equal to 0. So minimum typical maximum delay values discussed in gate level modeling at the end, right? So that also we can use in specifying the delay. Okay, so this is about the regular delay control. In example, the execution of a procedural assignment is delayed by the number specified by the delay control. For begin and groups, delay is always relative to time when the statement is encountered. Thus, y equal to 1 is executed 10 units after it is encountered in the activity flow. Only one example explained here, remaining it is shown there. Clear? Next, we will take the second part, which is the intra-assignment delay control. In the delay-based timing control, first one was regular delay control. Now this is intra-assignment. This is same as in data flow modeling. We have learned continuous assignment statement and intra-assignment statement, something internal, right? So that is this equivalent. Instead of specifying delay control to the left of the assignment, it is possible to assign a delay to the right of the assignment operator. So we have two types of assignment operator, right? Equal to or less than equal to. So now previous case I have shown the delay in the beginning, right? Left of the this operator. Okay, after that variable is written. Now after this assignment operator also you can mention the delay. Okay, this is called as intra-assignment delay control. Okay, such delay specification alter the flows of activity in a different manner. So by doing this, it looks like same, but it will alter the flow of activity in a Verilog compiler. Okay, so we'll show with an example here. So and also we'll explain what is the difference between intra-assignment and regular delays. So this is the example. Okay, so we have declared some variables x, y, z. Okay, initial begin. I have used the statements here x equal to 0, z equal to 0. So this is no delay. Okay, so then I have used a statement y equal to hash. See here, after the operator, I have used a delay hash phi equal to x plus z. If you write like this, so what is the change in flow of activity? Take value of x and z at time equal to 0. At the time instant 0 only, x and z will take the value 0 and 0 and it will do the 0 plus 0 operation. But evaluate x plus z at that time, but then wait for 5 time units to assign value to y. So it will wait for. Okay. So in regular delay, the complete statement will be delayed by 5 minutes, 10 units, 10 time units. But now the expression part will be evaluated at the 0 time instant, but the assignment will take the late. So that is a splitting of the execution will happen here. So the same method, if we use regular delay, what will happen? So there is a temporary variable concept will come into picture. Okay, so the same method, the same example we'll try to show you with equivalent method with temporary variables and regular delay control. To show this is because to give you a difference between the two types. Okay. Initial begin x equal to 0, z equal to 0. We need to use a temporary variable. Temporary x z we have used. So where it will do the x plus z, and then you can use the regular. So this is the regular delay. Okay. So regular delay means it will delay the complete statement by a 5 10 minutes. Okay. So if it is written without this statement, okay. So straight away if it is written x plus z here, so then even the x plus z computation will also happen at the 5 time minutes. Okay. And assignment also happens after that. But now because of this, what will happen? So at 0 time instant, so temp xz will have the value of x plus z, and then it will be computed at that time, but assignment will happen at 5 time minutes, which is same as intra assignment delay, by just writing the this as 5 after the equal to operator here. Okay. So take value of x plus z at the current time and store it in a temporary variable. Even though x and z might change between 0 and 5, the value assigned to y at time 5 is unaffected. Okay. So this is to show you equivalent to the intra assignment delay. Okay. So now we'll just summarize what is the difference between the two. So intra-assignment delay and regular delays difference. Regular delays defer the execution of the entire assignment. Regular delays, it will delay the execution of the entire assignment, whereas intra-assignment delays compute the right-hand side expression, RHS expression at the current time, that is 0 time, and defer the assignment of the computed value to the left-hand side variable. Okay, so assignment it will make delay. And another thing is intra-assignment delays are like using regular delays with a temporary variable. At last we have shown, right, to store the current value of a right-hand side expression. Okay. So this is about the difference of using the two delays in delay-based timing control. So now one more we will consider, that is zero delay control in delay-based timing control. So procedural statements in different always initial blocks may be evaluated at the same simulation time. Okay, so as we have mentioned, if you write multiple initial, multiple always block, all will start the evaluation at the same time, but the completion maybe takes different time, that we have mentioned. The order of execution of these statements in different always initial blocks is non-deterministic. So here, which initial will take? So because all at the 0, no. So when 0 means there is a confusion, right? So if you say all the 10 are first rank, means it is a non-deterministic. We could not say, right? So always one will be the topper, or one or two will be the topper, not all, right? And not all will be failing, right? Not all will be taking the same marks. It is undeterministic. The same way this execution happens at the 0 time unit. Okay. So that's why zero delay control is a method to ensure that a statement is executed last. Just to make this statement should be executed last, we will exercise zero relay control, and it is not any practical use. Okay, not a recommended practice, just to show you or that concept we are discussing here. Okay, after all other statements in that simulation time are executed. Okay, so to exercise that, to execute last, zero delay control is used. This is used to eliminate race conditions, as in earlier we have considered, right? Race conditions, both will try to take the value at the same time. Swapping of the variables example I have considered, right? So to eliminate that, this is exercised in behavioral modeling. Okay, don't confuse with different modeling style. However, if there are multiple zero delay statements, the order between them is non-deterministic. It is not going to solve complete 100% solution, only 50%, because again if you specify zero delay control to multiple statements, again their execution is non-deterministic. Okay, so it is just a theory, just will understand by an example. Example is the more clear picture it will give you about the concept. So see here, there is an example here. Initial block is written, begin x equal to 0, y equal to 0, end, one block. Okay, then again you have initial begin. So here zero delay control is exercised. This is as 0 means zero delay control. Okay, so just specifying as 0. So this is one initial block. This will also start execution at 0 time, and this also start execution at 0 time. But which one will do first? It is undeterministic. Okay, but since we have exercised zero delay control, so these statements will be executed last. Okay, that means x equal to 0 and y equal to 0 is executed first. Again, which one will execute first? Undeterministic. Okay. And similarly here, zero delay control is specified to both the statements. Again here, x equal to 1 will execute or y equal to 1 will execute first. Again, it is non-deterministic. But compared to this one, so this will execute next. Only that we can explain by zero delay control. Clear? So in example, four statements x equal to 0, y equal to 0, x equal to 1 and y equal to 1 are to be executed at simulation time 0. However, since x equal to 1 and y equal to 1 have hash 0, they will be executed last because it is called as zero delay control. Thus, at the end of time 0, x will have value 1 and y will have value 1. Okay. The order in which x equal to 1 and y equal to 1 are executed is not deterministic. Okay, so in the same example, if you given hash 0 for this statement, okay, x equal to 0, y equal to 0, then the final value, this will be executed last. No, first it would have taken x equal to 1, y equal to 1, then it is updated to x equal to 0, y equal to 0. That is what the meaning here. Okay, so they will have a final value 1. Okay, because we have exercised on these statements. If you exercise the zero delay control on first block, then it would have answer 0 here. Okay. The above example was used as an illustration. However, using hash 0 is not a recommended practice. Okay, so just to show you how zero delay control concept has come and how it is used. Okay, so that completes the first part of the timing control, delay based timing control. So now we'll take up the second part, event based timing control. An event is the change in the value on a register or a net. Okay, so when you have given two inputs a b 0 0, if there is a event happens on b, that is 0 changes from 0 to 1, that is a event. Okay, or it is a change in the value on a register or a net, that we call it as the event. Okay, events can be utilized to trigger execution of a statement or a block of statements, that is like a condition. Okay, so if this bit is 0, do like this. Okay, that is the event triggers the execution of a statement. So there are four types of event based timing controls are there, four subtypes. Okay, one by one we'll see this. Same as first one, regular delay control, we have regular event control. Then these are new things, named event control, then event or control, and finally edge sensitive control. Okay, so each of this will define and will exercise with the examples. Okay, so how they are exactly working. Okay. So this will give you clear picture about behavioral modeling statements. So the regular event control. So regular event control will use a @ symbol. @ symbol is used to specify an event control in regular. So by default, whatever we have seen so far, always initial blocks, initial it will not use, always block. So it will be @ symbol. Okay. So statements can be executed on changes in the signal value or at a positive or negative transition of the signal value. Okay. So the keyword pause edge is used for a positive transition as shown in example below. Okay. So like pause edge, negative edge, the keywords will be used here to just to make the event happening. Okay, so event. So examples we'll see, there are many examples. One example is in this slide. So @ clock q equal to d, if you write like this, what is meant by this? Q equal to d is executed whenever signal clock changes value. This is event. Okay, so clock may be 0 initially, so it will change the value. Okay, 1, then again 0. So in clock we will not call 0 and 1, we'll call it as positive edge. Okay, this is upward, and when it is falling we call it as negative edge. Okay, so that's why it is mentioned pause edge keyword. Okay, so in this example just I have mentioned clock changes, that means it may be 0 or it may be 1, any, so both it will change. Okay, it will change from 0 to 1, 1 to 0 also, this statement will execute. But if you write the same statement now, we'll modify the example. See here, if I write like pause edge of the clock q equal to d, so now q equal to d is executed whenever signal clock does positive transition. Okay, what is that positive transition? See here, this is the clock signal. If you consider, if there is any change in the value of the input, it will happen only during the positive edge. Negative edge it will not change. See here, all the positive edge. Okay, and that is defined as the value 0 The value of 0 changing from 0 to 1 x or z is called as the positive transition. X to 1 is also called as a positive transition, and z to 1 is also called as the positive transition. Okay, so all this you should know in detail. Similarly, if you use neg edge, so neg edge is the keyword for negative edge of the clock, q equal to d. Then q equal to d is executed whenever signal clock does a negative transition. So negative transition is falling, right, like this. Only during negative falling it will change the value. So negative edge trigger D flip flop, one program we have done right previously. So that is like this. So what is negative transition means? One value to 1 is the highest value, to 0 lowest value, intermediate x or z. Okay, all these are called as negative edge. Similarly, x to 0, x is some indeterminate value between 0 and 1. From there to it is coming 0 also negative edge. Z to 0 is also negative transition. So then like this also we can write q equal to at the rate positive edge of clock d. Okay, so this is also delays exercise. So d is evaluated immediately here at the 0 time instant, but assigned to q at the positive edge of clock. Okay, so when you write an operator after this assignment operator, so this will be read first, read operation, and while writing it will take this delay. So this is about the regular event control. Hope it is clear to you. So we'll consider the second one, named event control. Verilog provides the capability to declare an event and then trigger and recognize the occurrence of that event. Okay, you can name that event. Okay, that is named event control. The event does not hold any data. A named event is declared by the keyword event. So event is also a keyword just to name that event. Okay, an event is triggered by the symbol, this one. Okay, so hyphen then greater than symbol. Okay, so this is the symbol used to trigger the event. Triggering of the event is recognized by the symbol at the rate. Recognition will be done by this. Okay, so we'll see an example to understand this. Named event control. So this is an example of a data buffer storing data after the last packet of data has arrived. Okay, so for example, you have a 4 MB of video. Okay, at a time only 1 MB of video it can receive. Okay, so 4 MB to receive, how many packets are required? 4, right? 1 MB, 1 MB, 1 MB, 1 MB of 4 you need to receive. So that is the incidence here. So now we will declare event received data. Okay, so event received, event is the keyword and received data is the variable. Okay, so define an event called received data. Next, always at positive edge of clock. So this is the block of the behavioral modeling. That means you have to check every positive clock edge. Begin if last data packet. As I told you, 4 MB of data we are receiving. Okay, real-time application. So if it is named it 0, 1, 2, 3, maybe named it first one 1 MB, 2 MB, 3 MB, 4 MB, or it may be less than 4 MB. Okay, practically it is less than, no, last packet always, or it may be exactly same. So if it is received last data packet, this is the condition we are checking. Okay, so in case this is the first packet, it is a false statement, right? So it is keep continuing receiving the data. So once it is received the last data packet, if this is the last data packet, then trigger the event receive data. So to trigger that event, see here, this is the symbol used here. Okay, so this is about the named event control. Clear? Event name you can give and you can control exercise on that. Similarly, one more example. So this is the example, 4 MB data I told you, no, received data, await triggering of event received data. When event is triggered there in previous, so it will store all 4 packets of received data in data buffer. Okay, so use concatenation operator. So this is the concatenation operator here, lower bracket, and in between we have used the comma. Okay, so this is the concatenation. See here, this is 1 MB of data, this is another 1 MB, this is another 1 MB, this is another 1 MB. So total 4 MB of video is stored in now the place data buffer. This is how normally the things happens. Okay, because whatever you are using, mobile, laptop, everything is also digital circuits, right? So that's why you can analyze it very easily. Fine. So this is about the second named event control. Now we'll go for the next one, event or control. Okay, so this is a very important one because this is we are regularly using in our programs in lab also. So sometimes a transition on any one of the multiple signals or events can trigger the execution of a statement or a block of statements. Okay, so it can have multiple triggers, not only single one. Okay, so this is expressed as an OR of events. OR means everything, it will inclusive, right? The list of events or signals expressed as an OR is also known as sensitivity list. Whatever you write with OR, okay, so how many signals you will write, that is called as the sensitivity list. And the keyword OR is used to specify multiple triggers as shown in example below. Okay, so we'll see that with a event OR control. So see here, a level sensitive latch with asynchronous reset is the program. Okay, always at, see here, reset is one of the variable, clock is another variable, d is another variable. So in between, to differentiate, we have used OR. This is called as event OR control. Okay, you have seen maybe previously always with comma, that part I will consider next after this. Okay, but OR also can be used. Okay, so this is event OR control. That means it will depends on multiple triggers, not only one. It may be depend on positive edge of the clock. It may be depend on the reset also. It may be depend on the input delay also. Okay. So this is multiple trigger concept. Wait for reset or clock or D to change. That is the meaning. So this is called as the sensitivity list. Whatever you write inside this bracket, no. So this is called as a sensitivity list after at the rate. Begin if reset q equal to 1 bit 0. Okay, if reset signal is high, set q equal to 0. Else if clock q equal to d. If clock is high, latch the input like a D flip-flop. Okay, so this is the program. Okay, here important thing is here, this is explained here, event OR control. Now this same OR can be replaced by a comma operator. That's what I have shown you previously in all the examples. That is also called as event OR control. Sensitivity lists can also be specified using the comma operator, okay, instead of the OR operator. So example below shows how the above example can be rewritten using the comma operator. Comma operators can also be applied to sensitivity lists that have edge sensitive triggers. Okay, last concept we have edge sensitive control, there we will do that. Okay, so this the same program, no changes, only thing change here is in the always. Okay, see here, OR is removed, comma is placed, OR is removed, comma is placed. So this is the same meaning, wait for the reset or clock or D to change. Same program, the remaining part also same. Okay, so just you can use comma or. Normally I will use the comma, you have seen maybe so far wherever I have used always, I have not explained that part, right? Now it is the time to explain what is that sensitivity list. Okay, so this is it, means multiple triggers, only single trigger is there, we call it as named event control. So this is event OR control. Clear? Fine, we'll go for the one more example on this event OR control with comma operator. A positive edge trigger D flip-flop with asynchronous falling reset can be modeled as shown below. Okay, always at, see here, pause edge clock, you can use here like this also, positive edge of clock and negative edge of reset. So this is called as normally uh, asynchronous flip-flop. Okay, counter also we can design like this. Okay, one is taken at positive edge, another is negative edge. Okay, not synchronized. So if not of reset q equal to 0, else q equal to d. So this is the design of a D flip-flop. Okay, we'll learn it more in design part. Okay, how this program is written. Okay, so just by the truth table it is implemented. Okay, so in truth table what you have, a reset and clock will be there, and then output will be q. Okay, so this is what you have seen for D flip-flop. So clock will be positive edge. Okay, everything positive edge and negative edge of reset. So if reset is equal to 1, 1 means what, not of 1. So not of 1 is 0. So 0 means what, this will be executed. Okay, reset is 1, this one reset is 0 means not of 0 1. So this will be true statement will be executed. So this is the same way doing the design. So next one, it is edge sensitive control. Okay, the fourth type in the event OR control. Okay, so event based delay control. Okay, or timing control. When the number of input variables to a combination logic block are very large, sensitivity list can become very cumbersome to write. Okay, so when you have or like multiple 50 hundreds of thing or comma, every time putting comma, it is very difficult, right, in event or control to replace that. Moreover, if an input variable is missed from the sensitivity list, the block will not behave like a combinational logic block. In case in the number of 50, one of the things, human tendency, right, making mistake. Suddenly if you make mistake, so what will happen, it will not work like a proper design. To solve this problem, Verilog HDL contains two special symbols. Okay, at the rate star, or in bracket also you can use. Either this you can use or this. Both are same. So both symbols exhibit identical behavior. These special symbols, okay, these are special symbols, are sensitive to a change on any signal that may be read by the statement group that follows this symbol. Okay, so whatever you are writing inside that or, just if you write star, it is very sensitive now to any of the input changes. That's why it is called as edge sensitive control. So we'll show an example here to exercise the combination logic sensitivity list. So this is the example here. So combination logic block using the or operator, cumbersome to write and it is easy to miss one input to the block. See here, always at C. This is A or B or C or D or E or F, G or, so these many statements are there. And I have used one simple example, out one equal to A. Conditional operator I have used, B plus C, D plus E, F, G plus H, P plus M. So all the signals should be written here, because any of the values changes here, it will change the value of out 1 and out 2. So while writing this multiple ors, you may miss any one, right? Here it is written in proper order, A, B, C, D, E, F, G, H, P, M. But in case if it is a different value in real time, so it is difficult. So for that sake, we'll use the hash star operator. Okay, so that will show in next slide. So this is the regular program. So this can be replaced by now hash at the rate star. Okay, see this program. Instead of the above method, use as symbol. Alternatively, this symbol can be used. All input variables are automatically included in the sensitivity list. By default, whatever you have declared as input, it will come and sit over here. See here. So you can write just star, or in bracket you can write star. So this normally brackets will use in always. So this is the thing. Simple, no need to write or like multiple. So this is edge sensitive control. So this is the same program, just star we have written. Hope it is clear. Okay, so finally we'll come to the last type of timing control. We have seen delay based, event based, and this is level sensitive timing control. Level sensitive timing control is the ability to wait for a certain condition to be true before a statement or block of statements is executed. Okay, so it will have a wait for a certain condition to be true. So the keyword wait is used for level sensitive constructs. Okay, so each of the things you have to remember the keywords there or the symbols. Okay, that is very important. So here is level sensitivity is wait. Okay, see here, always instead of using it, we have used wait. Wait, what is wait? Count enable. Okay, count enable should be 1. Count enable should be 1. That is the indication. Okay, then delay is specified hash 20. Then expression is written, count equal to count plus 1. So this is about level sensitive. So just to explain this program, in the above example, the value of count enable is monitored continuously. If count enable is 0, the statement is not entered at all. Okay, so if it is logical 1, statement count equal to count plus 1 is executed after 20 time minutes. That is the condition. If count enable stays at 1, count will be incremented every 20 time minutes. So this is the thing about the level sensitive timing control. So with this we have completed the timing controls on behavioral modeling. So just to recall what we have learned, there are 3 types of timing controls. One is delay based timing control, event based timing control, and level sensitive timing control. Again, in regular delay based timing control, you have 3 subtypes: regular delay control, intra-assignment delay control, and zero delay control. Hope it is clear. And then event based timing control, you have regular event control, named event control, event or control, edge sensitive control, okay, timing control, and then finally you have level sensitive timing control. Okay, so just go through once again. So this is a new topic in behavioral modeling. Okay, so with this we'll end the session here on timing control. In the next video we will come up with another new topic in behavioral modeling. Okay, thank you.